the chemical plants, they typically consist of a number of chemical process units. A chemical plant includes a number of chemical process units. Just a few of them are reported here, like reactor, heat exchanger, pump, compressor, absorption column, desorption column, stripping column, distillation, evaporator tank, etc. So that's why we sometimes call it's a basically flow sheet of a chemical plant, because it includes so many process units. Then the second point you see the overall objective. So what is our overall objective? We usually introduce raw material to the chemical plant, and then after processing the raw material one after another in different process units, which I mentioned just above, finally we get desired products. I repeat, our overall objective is to introduce raw material or feed the raw material to the chemical plant, and then that raw material gets processed in different units one by another, or maybe parallel, and finally we get the desired product. But challenge is that we need to produce this desired product from the raw material in most economical way. We need to produce the desired products from raw materials in most economical way. Now, to meet this overall objective, we need to follow some requirements. I mean, there are some requirements involved in this whenever we are going to meet this overall objective. And these requirements are usually imposed by designers, engineers. I repeat, to meet this overall objective, there are several requirements involved, which are imposed by designers, engineers. Now we know these requirements one by one. So our first requirement is safety. Our first requirement is safety. The safe operation of a chemical plant is a primary requirement. Safe operation of a chemical plant is the primary requirement for the well-being of the operator involved in duty, and definitely for the continued contribution to the economic development of our nation. Safe operation of a chemical plant is the primary requirement for the well-being of the people in duty mainly, and definitely for the continued contribution to the economic development of our nation. Now, to ensure this safe operation, we need to maintain the operating variables. 3 examples you see I have given here. One is pressure P, temperature T, and concentration C. There are many more. It is basically specific to a particular process. So usually these are the common variables which we need to maintain within certain allowable limits. Fine, we need to maintain the operating variables within a allowable limit. Let us take one example of pressure vessel. In this regard, let us take one example of a pressure vessel. So pressure vessel, usually the gas, the compressed gas, they are stored in a pressure vessel, usually at very high pressure or low pressure. Suppose one pressure vessel is designed for maximum 100 atmospheric pressure. Listen carefully. A pressure vessel is designed for the maximum allowable pressure of 100 atmosphere. So we can say that this is the design pressure. Design pressure of the pressure vessel is 100 atmosphere. Now question is, what happens if the pressure exceeds 100 atmosphere? Anyone can give the answer? The design pressure of a pressure vessel is 100 atmosphere. This is the maximum allowable pressure. Now suddenly the pressure exceeds 100 atmosphere. What happens in that case?
It can explode.
Yes, exactly. So we need to operate the pressure vessel always below the design pressure. Now question is, who will maintain this pressure all the times? We need to operate the pressure vessel below the allowable limit, that is design pressure. Then naturally one question arises, who will maintain, who will check, who will verify this pressure all the times that it should be lower than 100 atmosphere? That's why the question you see in red color, how we can maintain this. Okay, keep this question. We'll discuss the answer later. Now next, second most important point is the production specifications. For a particular plant, we need to produce the desired quantity as well as quality of the products. If we get more quantity, then we can sell it in the market with more money. I mean, we can have more money if we have more product. That's why this quantity is there. Fine. But to produce more amount of product, we cannot compromise with the quality. There are certain market specifications on the quality. So we need to maintain that. Otherwise, we cannot get the proper price for our product. So there are two important issues under this heading, product specification. One is the quantity of the product and the desired quality of the product according to the market specification. Let us take one simple example in this regard. Suppose we need to produce 2,000 tons of ethanol per day with 99.5 mole % purity. Fine. This purity is set according to the market demand. This is almost pure ethanol. Okay. In fact, the ethanol which we are presently blending with our petroleum product, especially petrol, that purity is more than 99.5%. Now, again, the question is how you can maintain this quantity and quality quantity in day basis and quality all the times. How you can maintain? We'll take care of this. Do you have any other point in your mind which we need to satisfy? Anyone can give. I told 2 points. One is safety, another one is product specification. Anyone have any requirement, any point related to requirement?
Sir, can you repeat the question again?
I have given to mention 2 requirements. No, one is the safety, second one is production specification. Can you add any other requirement other than these 2? You give the answer, it may be wrong.
Instruments.
Instrument. Instrument means what? Are you talking about the cost, initial investment?
No, not the cost.
Then tell in a better way, maybe you can converse to the right answer.
We have to follow an economical way. Best.
Yes, this is definitely true. I mean, overall, ultimately there must be good amount of profit. Otherwise, no one is coming to invest.
And again, we should even check the amount of pollution that is being caused by the
Very good. What's your roll number?
19CH30018.
Sai, no? Yes, good. So next point is environmental regulations. You are very correct. You see, I have given few examples related to this. You note down this point. Our third point is related to environmental regulation. There are several federal and state laws which enforce us to maintain these standards, certain standards related to pollution. Concentration of chemicals. Suppose certain chemical is methylene blue, which is coming from one paint industry, that is directly rejected to say river. Like carbon dioxide, which is rejected to atmosphere, sulfur dioxide, which is rejected to atmosphere from refinery industry. There are almost everywhere, water is used, and that water we call as wastewater, which is simply rejected to either river or somewhere to canal, sea. But we cannot reject all these arbitrarily or as per our wish to the atmosphere or to the water. Now, again the question, how we can maintain this? We will maintain this all the times. I think you all understood this third point, right? And someone tell regarding the instrument. I think we can, somewhat represent that point like this: operational constraints. Okay. So there are equipments used with certain capacities, and definitely we maintain their operating condition with certain limits. So these are the typical examples which are specific to different chemical process units. Okay, so I think you are currently starting this distillation, no? In this semester, I think you have distillation. Am I right? Vivek? Vivek Sureka.
Yes, sir. Sir, your voice wasn't clear actually. Your question, I couldn't get your question.
My question is distillation, I think you did not study, no? Anyway, I think distillation you have in this current semester. So, in the distillation column, there are several trays. On the tray, there are liquid and vapor mixes which are in contact. So, if distillation tray is flooded, definitely the separation efficiency gets hampered. So, we need to avoid this flooding. Second example is catalytic reactor temperature. It should not exceed upper limit. Reason is given there. Catalyst may be destroyed. Catalyst gets deactivated. Third point is tank should not overflow or go dry. Usually the tank, suppose it contains certain amount of liquid, and one pump is usually used to deliver the liquid to a processing unit. So you are understanding if the tank is dry, so the pump is not
Sir,
getting
your voice
anything.
is not clear.
Not clear. So you understood these points or not?
Sir, actually, your voice is breaking a little bit. So we
Yeah, I understood.
understood a
I
bit.
understood.
There's a lot of confusion actually.
See, I don't know, perhaps today is a first class, so we are facing some problem because of, overload after a long time. So what is NPSH?
Sir, it is the net positive suction head.
Yes. So we need to maintain that, no, NPSH.
Yes, sir.
Okay. Now the last point is also one of your friends told regarding this point. I mean, this point is mainly saying that we need to minimize the operating cost. And definitely at the same time, we need to maximize the profit. This is the last point. Above all, profit is, is very important part for the investment. So in the second line, you'll see this capital means capital investment. When you are going to invest money for one industrial unit, at first we need to invest money for the equipment. Say, we are not discussing about land and other issues. We are completely, concentrating on the chemical plant. So that is capital investment. Then after that, we need to introduce, as I mentioned, raw material. Okay. Then there is certain operating cost which involves the energy. That means we need the electricity, we need sometimes cooling water, we need steam, etc. All these utilities fall under this energy. Right? Or you can simply replace this. Better term is utility. Then definitely we need to involve the labors, human labors, and operators, engineers, they all are there. So this is the last point. Now in all 5 points, I have one question, that is how we can do this. Anyone have the answer of this question, how? Anyone can give the answer of this question, how?
So could you repeat it?
Yeah, in the last 5 points, I have one common question. Fine. That is how. My question is, what is the answer of this question? How? How you can maintain all these requirements? Who will maintain this at all time instant? Okay, so answer is in controller. Answer is in controller. That means controller can take care of all these issues. It can address all these issues. So that's why we are interested to read this, process control. Let us come to discuss first why we need this controller. Okay, what is the motivation behind this? For this, we will take one example. You first draw this process unit, heating tank system. We draw the heating tank system, then we'll discuss what is the need of a controller. Fine, I think you have drawn this. So you see in this process, F is basically the flow rate. We denote the volumetric flow rate by capital F, and suffix I indicates the input. F represents the flow rate and suffix I represents the input. So the inlet flow rate that has, the inlet stream has a Fi flow rate and temperature TL. Now there is one starter mainly to maintain the temperature uniform in this heating tank system. T is temperature and H is height. Outlet stream has flow rate capital F and temperature T. Now to heat this liquid up, we are using one steam which is flowing through a coil. You see, steam is flowing through a coil. Fine. Now, whenever you are taking one example in this course, the first point should come to your mind is that what is the control objective of this process? I repeat, whenever you are taking an example in this process control course, the first point should come to your mind that what is the control objective of this process? Like for this example process, I have written in the right hand side, you see the control objectives. We want to maintain the temperature T in its desired temperature. Desired temperature means set point. SET. That's why suffix SE. I repeat, our first objective is to maintain the temperature of the heating tank system T at its desired value, that is T suffix SE. SE means set point. It is set by you or the operator. Fine. Suppose we want to maintain the temperature of the heating tank system at 100 degrees Celsius. That is my wish. That means our set point temperature is 100. And how much originally attained here, that is capital T. So if these two are identical, then we can say that our objective is completely met. The second control objective is the liquid height in the tank, H. And that's why it is written the height H should be equal to its desired height, that is H suffix SE. Agree? Now another point you remember, which is written in the green color here, open loop system. So basically in process control course, there are two types of systems. One is open loop system, another one is closed loop system. Very straightforward definition is that open loop system means it is only the example system. There is no controller involved. Fine. So open loop system means the process without controller. And closed loop system means process with controller, which I am going to show in the next schematic. I repeat, open loop system means system without controller. And closed loop system means system with controller. Okay. Now, before going to the closed loop system, before going to discuss that, let us note down one point, this one. So initially, when you are going to start a point, when you are going to start a particular process, we do not have steady state. So our first work is to start a process and bring the process to steady state condition. After reaching steady state condition SS, you can employ the controller. I repeat the point, you have one process, you just start the process. At the starting, you do not have steady state. Fine. So what we need to do, we bring that process from startup to steady state condition, which I have represented by SS. SS means steady state. So after achieving the steady state condition, you can only use the controller. This is the general, concept. Now, point is that if your process is always at steady state condition, then there is no controller. There is no need of any controller. If your process remains all the times at steady state, then we do not need any controller. But point here is that in industrial process unit, there are several external disturbances. So as a result, our process never stay at steady state. It always tries to deviate from the steady state. Because of this, we need controller in practice. Got this? If our process remains at steady state, then there is no need of any controller. But in practice, there are several external disturbances which are usually or continuously disturbing the process. As a result, the process starts deviating from steady state. Fine. Now, to prevent this deviation, we need one controller. I am just giving you one simple example for disturbance. Suppose there is an overhead tank from which the liquid is coming to this heating tank system. I did not show here any tank. Suppose there is an overhead tank here from which this Fi is coming to this heating tank system. Now you think about this temperature of the overhead tank. At morning, temperature is low. In afternoon, the temperature rises. And again at evening, the temperature decreases. So for an overhead tank from which the liquid is coming to this heating tank system, for that this Ti varies throughout the day and night, over the day. So that is basically considered as disturbance. And because of this disturbance, this temperature basically changes from its steady state value. Fine. Now let us come to a general concept. So here we want to calculate one error signal, which we are representing by small e. Small e is basically the error. This error is nothing but the set point value minus the measured temperature, capital T. This error signal E is set point value minus temperature. This you are going to set, and this temperature we are getting from the process through measurement. Now you think physically, when this error is greater than 0, what does it mean? Set point temperature is greater than the temperature, existing temperature. So how you can maintain TSP equal to T? We need to introduce more steam. Fine. In this particular process, if the temperature decreases, you introduce more steam to this coil. Then only we can raise this temperature. In contrary, if this temperature decreases, we need to increase it. That means we introduce more steam. If temperature increases, you reduce this steam inflow rate. This is the concept. And this is taken care of by the controller. Got this point? If error is greater than 0, that means set point temperature is more than the existing temperature. In that case, we need to introduce more steam. In contrary, if error decreases, it is less than 0, in that case, our temperature is greater than set point. So we need to reduce the steam flow rate. Palak Agarwal, understood this? Palak? No response. Samira Yasmin? Samira Yasmin? Sayan Maiti?
Yes, sir.
Understood?
Yes, sir.
Good. So let us come to the closed loop system. You first draw it. You first draw the process, open loop process. Okay. Just repeat the previous drawing. Then I will discuss how to configure the control scheme. So let me discuss this. Initially, you have the open loop process. That means this one you have. Okay, now we want to configure the control scheme. How we can do that? Initially, we want to measure this temperature, you see, by employing one sensor. You remember this concept will be used throughout this course. I repeat, in the first point, you draw the open loop process, which is shown before. As a second point, we want to our control objective is fixed. That is, we want to maintain the temperature. So for that, we need to measure the temperature. How we can measure the temperature? By employing one temperature sensor. Okay, so this is the sensor. What is the output of the sensor? Temperature T, you see, which is shown through this arrow. Temperature T. Now, since we want to calculate the error I have shown TSP minus T. That's why you see this temperature carries the negative sign. And set point value you need to set or operator needs to set, and it is plus sign. So yeah, can you hear me, students?
Yes, sir.
Yes, sir.
Okay. Yeah, so this is the error signal, and you note down this one. This one is called comparator. This one is called comparator. It basically compares the set point with the measured signal temperature. So error equation I have given before, that is TSP minus T. You are understanding from the sign also. Then the error signal goes to the control block. This controller is nothing but a PC, computer, where your programming is written there. This controller is nothing but a PC in which you have written all the programs. What programs? The calculation of this steam flow rate. Fine. So after getting this error signal, the program will compute, or better to say the controller will compute this steam flow rate. Then that we call as control action. That control action is finally implemented through this valve. Originally, this is control valve. You can note down this. This is a control valve. Okay. Now, through this control valve, I am changing the control valve opening. The steam flow rate is maintained. I repeat these important points. Initially, you draw this open loop process. In the second point, you fix the control objectives. Like for this particular example, our control objective is to maintain the temperature at its desired level. Do not consider height. Let us consider first simply the temperature. Now, how we can do that? So, first we need to measure the temperature. For any variable like temperature, like height, like pressure, you can simply write here sensor. So in case of temperature, it is basically temperature sensor. In case of pressure, it is pressure sensor, like that. Okay. Until and unless it is discussed in this course, you just write here sensor. Now, what is the output of this sensor? Temperature. Basically, this is measured temperature. It carries negative sign, and there is set point which is fixed by you or maybe the operator, which carries negative sign. Then this block is basically the comparator. This comparator compares a set point minus T. That is error signal, which is denoted by small e. This error signal goes to the controller. Then controller calculates the control action. Then this control action is physically implemented through this control valve. It basically estimates the opening of this control valve. If we need to introduce more amount of steam, then you have to fix the opening like that way. If you want to reduce opening, accordingly will be fixed. So by this way, we can maintain the temperature. Fine. So since this process includes a control configuration, that's why it is called closed loop system. But students, you remember this is control configuration. I'll use some specific terms and do not be confused with the terms. Okay. This is control configuration, this one. You note down this control configuration, because it is coming in the exam asking that you draw the control configuration. Sometimes the student are drawing the control block, but that is completely different. Fine. Now you see this sensor and this valve, these both fall under instrumentation part. And this controller plus comparator, they fall under process control part. So the name of this course is instrumentation and process control. No? So it has clearly two parts. Instrumentation part includes this control valve as well as sensor, temperature sensor, pressure sensor, height sensor. Okay, all these will be discussed under this. And this comparator and controller part will be discussed in the process control part. So I will mainly cover this process control part, and Professor Chakraborty will cover this instrumentation part. So by this way, you can divide this course. Do you have any question? If you have any question, you can ask me.
Sir, I just wanted to clarify whether this figure stands for a stirrer in between T and H inside the tank.
Here, stirrer is, why we use, you are asking, or what?
No, sir, I just wanted to know what that signifies, that particular figure.
This one?
Yes, sir. Yes, sir.
Stirrer is used to maintain the temperature uniform in this tank.
Okay, sir.
Okay. Like here coil is present, no? So naturally temperature will be higher here, no, than this one or somewhere else.
Yes, sir.
Just to maintain the uniformity in temperature as well as concentration, we use a stirrer.
Okay, sir.
Any other question, anyone? Okay, I think you all understood this. Now, question is why we should go for controller. We have taken one example now, but what is the need of this controller? You know, down these 3 points, so we'll discuss one by one. Why we need to use a controller? First one is to suppress the influence of external disturbance. Second one is to ensure the stability. And third one is to optimize the performance of a process. That means we want to find an optimal condition at which we get the best performance from a process. I repeat, the third point is we want to find And we want to find an optimal operating condition at which we can have the best performance from the process. Now we'll discuss one by one these issues. Suppressing the influence of external disturbance, stability. Okay, let us cover the first point. Influence of external disturbance. So for that, we will take a simple example. Just draw it. Let us discuss the first issue, that is influence of external disturbance and how the controller plays its role in resetting the effect of external disturbance. We want to see how the controller rejects the effect of external disturbance. If you think physically, you can easily understand this. You see, if I increase the inlet flow rate, what happens? Naturally, the height increases. And as a result, the height becomes higher than its set point. You can easily understand if you physically think. Like, if we increase the inlet flow rate Fi, height of liquid in the tank H increases. And it becomes more than the set point value. This is a reverse case. If inflow rate decreases, height decreases, and set point becomes more than the height. Okay. Now you just draw the configuration in a similar fashion. Draw the configuration which we did for liquid tank system. This is a control configuration. Okay. For this particular process, our control objective is to maintain the height at its desired value HSP. I mentioned before, for a particular process in this course, at first you would need to identify the control objective. For this liquid tank system, our control objective is to maintain the height at its desired value, that is HSP. So for this, we are first measuring the height using differential pressure cell. You note down this. DPC means differential pressure cell. Differential pressure cell. It is very simple. On the equation, del P equal to H rho G. So it basically computes the pressure difference, del P equal to H rho G. So from that we can easily calculate height H. Based on this concept, this DPC is made. The measure height is going to comparator. It compare with its set point value. The error signal goes to controller. Controller calculates its control action, and the control action is physically implemented through this control path. It's very similar, the control configuration. So let us come to the first point. If Fi increases, height increases. That means height becomes greater than H SP. But we want to make them equal. How we can do that? If height increases, we need to reduce this height so that we can get HSP equal to H. How we can do that? Just by increasing this F. Got? I repeat, if inflow rate increases, height increases. So it becomes greater than set point. but we need to make them equal. So how we can make them equal? Just you increase the outlet flow rate. And this is the reverse case. So by this way, we can reduce the effect of disturbance by employing a controller. Yeah, I think time is over. If you have any question, doubt, you can ask me now.
So could you please repeat what is the control configuration in this figure?
Yeah, you see, I need to explain.
No, so I just wanted to know which combination denotes the control configuration. Is it just the sensor and
This
the bar
one.
or the whole
This one,
thing?
this configuration.
Okay, sir.
Sensor, controller, and operator. Comparator. See, this is the additional part. No, if you compare with open loop process, this is the additional part. So this is control configuration.
Okay, sir.
Sir, is it possible to attach the controller to the input?
Yes, it is also possible. We'll discuss that, in fact, in the next class, perhaps. It is possible. In that case, Fi is not disturbance, remember.
Okay, sir. Thank you, sir.
We'll discuss that combination also later. Anyone else? Any question?
So is there any book you can suggest for this course?
Yeah, I'll send through your email. Okay.
Okay.
All the references. And if you have any confusion, I think you all know there is NPTEL course.
Okay,
NPTEL course. You can go through that.
Okay,
Okay.
sir.
Instrumentation and process control. In fact, we taught that course. So if you have any confusion, doubt, you can also go through that. Okay, then you can leave. Thank you.
Thank you, sir.
Sir.
Thank you.
Thank you, sir.